Yeah, so after we find the y-intercept, find the derivatives, we'll look for critical points. And then I've kind of given you guys a table to help you structure your second derivative test. Remember, we learned that yesterday, and I have it on the front board over here. So if you find a critical point and the second derivative is positive at that point, well, that must be concave up and it's a local min. If the second derivative is negative at that point, it must be concave down and be a local max. What we have to investigate later today is if the second derivative is zero, we have to look at what happens there, because sometimes many different things can happen. And then we'll find some inflection points as well. So I'll give you a little more of a head start. Maybe I'll just get my attendance done real quick. Sure, pause the recording. All right, and we're back. So y-intercept, the constant term is just zero here. Or you can show that work, but plugging in zero just gives you zero. So I guess we do know one intercept. It's an x-intercept. It's the same as the y-intercept. We go through 0, 0. So when you guys are sketching curves now, it should just be automatic. Find the first derivative, find the second derivative, and might as well do those back to back when they're polynomial functions. So what do we got? We got 12x cubed minus 24x squared minus 12x plus 24. And the second derivative, 36x squared minus 48x minus 12. I don't think we need to spend too much time on those derivatives anymore. All right, and then your next step is looking for critical points. So we're setting the first derivative to 0 and solving. So we're going to be mixing in some strategies from earlier grades. So one property you guys know is that if we have a common factor, we can divide this whole equation by that common factor and just make the number smaller, since 0 divided by anything is a 0. So I'm just going to add a little note here. I'm going to just divide by 12 just to make the solving easier. The number's a lot smaller. So we have x cubed minus 2x squared minus x plus 2 equals 0. I wouldn't feel bad having you guys solve this equation on any evaluation, because you guys all passed the grade 12 functions course. You guys learned the factor theorem. You learned polynomial division. You could apply that here, and everybody here could factor this one. But maybe let's mix in a skill from grade 10. If we don't have to apply the factor theorem and do division, then maybe we shouldn't. This one can actually be solved by group factoring. When a polynomial has 4 terms, sometimes you can reach for that tool. That's where you common factor each pair. And if you common factor the first pair, taking out x squared, you're left with x minus 2. And you'll notice if you divide out a negative 1 from the second pair, you also get x minus 2. And then x minus 2 is a common factor from each of those two parts. And what's left over is x squared minus 1. So it can be a handy little tool. Of course, you could still do factor theorem and whatnot. And of course, x squared minus 1 is a difference of squares. So we can factor that as x plus 1 times x minus 1. And now we have our three critical numbers. I'll say this. I'll say we have critical points at x equals, looks like plus and minus 1, and also 2. Yeah, I can't apologize for it. Just solving a polynomial equation like this, we have to be able to do it once in a while in the calculus course. There's just one more strategy. Group factoring worked in this case. But yeah, now I have a nice little table for you guys. I'm just going to put my critical numbers in order. So -1, x equals 1, and x equals 2. So can you guys fill in the rest of the table? Can you get the y value at those critical numbers? Can you get the value of the second derivative at those critical numbers? And then can you classify those 3 points? So they're going to be local max, local mins. or are we unsure? So I'll give you guys a bit of time to crunch those numbers. And yeah, as you guys do that, as you find points, add them to your graph. When you classify the points, look at your graph and see if everything fits together. And if things start to not fit, then that's a clue that maybe you went back, you did something wrong. You can go back and find it. If you sit beside somebody or with a group of people, you can share the number crunching. Somebody can do x equals -1. Somebody can do 1. Somebody can do 2. Three plus 8 minus 6 minus 24. I do my y values first. -5, -11, 13. For 2, that's 48 minus 64 minus 24 plus 48, 8. So I got 3 critical points, -1, -19, 1, 13, and 2, 8. I'm going to add them to my graph as best I can. -1, -19, 1, 13, right about there, and 2, 8, right about there. And I will say, you guys know how to look at end behavior for polynomials. You could probably just reason out which ones are local maxes and mins right now. But let's give our second derivative test a spin. So what was the second derivative? It was 36x squared. So 36 plus 48 minus 12 is 72. All right, critical point. Second derivative is positive. If you need to draw this visual that it's concave up, do that. But we've just shown, okay, this point is for sure a local min. You guys buying what I'm selling there? All right, you guys finish off the last two, and then we'll find the inflection points together. I'll have a sip of coffee while you do that. At 1, we would have 36 minus 60, so minus 24, which means it's concave down, which means a local max. And then at 2, too early for that multiplication. 144 minus 96 minus 12, 36. So from left to right, the critical points, I got local min, local max, local min. Do you guys get that too? But that already fits with everything you guys know. This is an even degree polynomial with a positive leading coefficient. So its end behavior is like a polynomial, or is like a quadratic function that opens up. And so we'll go down to this local min, back up to this local max, to this local min, and back up again. That would be a great sketch. We can add one more bit of detail. We can now, after yesterday, find some inflection points. So let's set that second derivative to 0 and look for some inflection points here. So do the second derivative equals to 0. And that second derivative was 36x squared minus 48x minus 12. I think that was it. Yep. All right, it's just a quadratic equation. We can solve by factoring. If you can factor, you can solve using the quadratic formula. It should just be automatic at this point in our math careers. That said, though, dividing by 12 will just make the numbers much more manageable to work with. I can see, because I teach factoring like 3 times a year to 3 different classes, and I've done that for like 16 years now. This one cannot be factored. Sometimes we just need to reach for the quadratic formula. If you have if you have a button on your calculator that just solves quadratic equations for you, I don't mind that. I'm kind of beyond evaluating if you guys can use the quadratic formula. Just make sure that it works properly. I'm gonna actually just show a little bit of work using the formula. So negative b, so 4 plus or minus the root of the discriminant b squared minus 4ac would be 16 plus 12 root of 28 over 2a, which is a 6. So I'm just using the quadratic formula. We don't need to spend a lot of class time talking about how to use the quadratic formula. But this gives you two values where the second derivative is 0. Let's find them. There'll be decimal values. I'll go to a couple decimal places. So we got 4 minus root 28, and then divided by 6. Does anyone have a calculator that can do that? Let's see some nods. Okay. I'm sure this one could too. I have never learned how to do that. So 4 plus root 28 divided by 6. So 1.55. Let's find those y values, plot them on the graph, make sure they fit, and then have a discussion on how we know these are actually inflection points. All right. Oh, that's not going to be fun to plug in. Okay. If you guys want to do the 1.55, I can do the negative 0.221. Minus 8 times negative 0.22 cubed minus 6 times 0.22 squared.
My calculator can use the quadratic equation.
Perfect.
I got the same answers, but the 1.55 is negative and 0.22 is positive.
Double check what you punched in then. I got the same numbers that I've got when I did my note before. I can also come by and see what's up with the calculator, but yeah, these are checking out. So when I plug in minus 0.22, I got about minus 5.5 for when we graph it. What did you guys get for 1.55? 10.3 seems reasonable. And let's add those to our graph. So remember, local min is down here, so concave up. This is local max, concave down. Somewhere in between, we need to change concavity, and that happens at negative 0.22, negative 5.5. Seems to fit really good, right? Everything we're plotting on our graph is making sense so far. So an inflection point, negative 0.22, negative 5.5 as best we can. And I'm just going to label that an inflection point for when I'm graphing. And then our second inflection point, so we go from a local max to a local min. And right in the middle at 1.55, 10.3, right about here, something like that, we expect another inflection point, and we got it. Everything's fitting together. Let's finish our sketch and then just have a conversation about how we know those are inflection points. So when you guys are sketching, after you found those critical points and classified them, this isn't like mandatory or anything, but sometimes it can help if that's a local min, just put a little teeny tiny concave up portion of the graph there, and same with the max and min. It can just help you visualize the shape. And then now we can see the points where we change concavity as well. And now we can kind of finish our sketch. A really nice detailed sketch of this polynomial function. So let's test out the fine motor skills. So concave up to the inflection point. That's fine. I'll just, you know what though? It looks kind of vertical, which is naughty. I can do better. If I stick my tongue out, that might help. Okay, that's okay. So concave up to that point, and then concave down to this inflection point, and then concave up forever and ever, amen, this way. So there we go. You guys okay with what we've done so far? So this is kind of the expectation after all the stuff we've done. We did a lesson on critical points. We can now find them. We did a lesson on the second derivative test. You can classify them. You can search for inflection points. But why are those 2 points inflection points? If you guys just dial in on 3x squared minus 4x minus 1. We don't need to make a perfect sketch of that to understand what it looks like. I'm going to make a sketch of that second derivative just down here where I have a teeny tiny bit of space. So just to be clear, I'm plotting the second derivative here. That is a quadratic function that opens up, right, because of the 3. And it's a quadratic function that has 2 x-intercepts. We found them, right? Negative 0.22 and 1.5. So would you guys agree that that parabola looks something like that? That's what the graph of the second derivative looked like, right? It opens up 2 x-intercepts. So how do we know these are inflection points? Well, look at the graph of the second derivative. It's positive to the left of negative 0.22. So the second derivative is positive. So concave up. When you get to negative 0.22, it switches to concave down. And then when you get to 1.55, it crosses again and it's positive. We're back to concave up again. So we can reason out that the graph changes concavity just by knowing our grade 10 stuff about quadratic functions. Is that reasoning okay with you guys? We can clearly see passes through, so it's changing concavity from positive to negative to positive. So we know that they're inflection points. Okay? So if you're going back and just looking at your note, maybe this isn't entirely helpful, but we had this whole conversation, and I'm actually recording this. I'll be posting this to the newsfeed afterwards. All right. You guys sure you're okay? This is kind of the level we should be at, being able to sketch a polynomial function, all those details. All right, then. We're going to finish up yesterday's note with a couple examples. Andrew, I think you need... Yeah. I think I got a copy. You guys want to look at it? It shouldn't take too long. Here you go. Yep. All right, enhance. All right. Okay, I'll get you a copy. Here you go. And introduce a warm-up convention too. All right, we're gonna have lots of time after this. All right, so this first example is gonna illustrate what happens when you're trying to graph a function and the second derivative is 0 and the first derivative is 0. It's gonna explain why we can't really draw any conclusions. So I know that you guys probably know what the basic quartic function looks like from your last course. And I also understand it'd be pretty easy for us to plug in a few values, make a table of values and sketch this graph. But let's just go in blind and apply the algorithm we've been using and just see what the math tells us. And then afterwards, we'll make the sketch and make some connections, if you guys are okay with that. So let's just suspend any prior knowledge of this function and just start doing the math and see what kind of pops out. So if you guys were making this, sketching this function, you'd start by looking at the intercepts. Those are often easy points to help give you guys some shape. So I'll just get that out of the way, maybe up here. Let's just make a little note. The only intercept is 0, 0. So again, we're going in blind and we're just applying our algorithm for sketching. We look for intercepts. F at 0 equals 0. It's the y-intercept. It's also the only value that makes the function 0. It's the x-intercept. It's the only intercept. You guys convinced? So you'd look for x-intercepts. And then you'd find the derivatives and start looking for critical points. So let's find our derivatives here. So f prime x is equal to 4x cubed. And the second derivative is equal to 12x squared. And then you'd continue your algorithm for sketching. And so you'd ask, okay, let's look for critical points. I might even put a little header here. We're looking for critical points. For critical points, we set that first derivative equal to 0 and solve. So we're setting 4x cubed equal to 0 and solving. And it doesn't take a lot of work to see that the only critical point is x equals 0. You guys mind that? It's the only critical point, right? X equals 0. Well, let's try to classify it. We already know the y value, but I'll just jot it down here. So f at 0 equals 0. That gives us the y value. The second derivative, though, when you plug in 0, the second derivative is 12x squared. And when you plug 0 into 12x squared, you also get 0. So this is kind of a new case for us. In the warm-up question, whenever we plugged our critical number into the second derivative, it was either, okay, this is concave up, it's local min, or this is concave down, it's a local maximum. But in this case, we got that f, the second derivative, is 0. So this is important. As much as we'd like to maybe say, hey, this is an inflection point, this is important. Can you guys jot this down? When a critical point also has a second derivative being 0, no conclusions can be made. You can't make any conclusions. More investigation is necessary. So we've kind of done all we can with the critical points. Let's go and keep applying our algorithm, and let's search for inflection points using the second derivative. So you guys would set the second derivative equal to 0. So 12x squared equals to 0. So we get x is equal to 0. Is x equals 0 an inflection point? Well, we have to make sure that at that point, the graph changes concavity. Can you guys, let's pick a couple test points. Can you guys find the value of the second derivative? So we're testing for concavity here. What's the value of the second derivative to the left of that critical number 0? And what's the value of the second derivative to the right? We'll use some nice test values of -1 and 1. The second derivative is 12x squared. Pretty easy to plug in. Do we not get 12 for both? We get 12 for both, right? Positive for both. What does that mean? Well, if we get a positive value, that means on the left of x equals 0, it's concave up. To the right of x equals 0, it's also concave up. So we actually now can make some conclusions. That point 0, 0, on the left it's concave up, on the right it's concave up. So does anyone want to volunteer? What do we now know about this? Is it a local min, a local max, or an inflection point if it's concave up on both sides? Zane? It's a local min, exactly. So we have now, after a bit more investigation, we can see that 0, 0 is actually going to be a local minimum. But that second derivative test wasn't enough. We had to dig a little deeper. We looked at that concavity on either side this time. Now, if I may, can you guys, since I have some space, and then we'll graph the function and we'll make sure everything fits. 12x squared is a function you guys should just kind of know what it looks like. We can make a simple sketch here of this second derivative. It's a parabola. It opens up. Its vertex is at 0, 0. It looks like that. If you think about the concavity of this function, f of x equals x to the power 4, the second derivative is always positive, except at 0 where it's 0. But if the second derivative is always positive, this function is always concave up. There's going to be no inflection points changing from concave up to down. It's always going to be concave up. So that's how we knew. Another reason why we knew x equals 0 wasn't an inflection point but we had to dig a bit deeper. We had to look at the concavity of each side. Now let's actually just sketch this function. And again, you guys, I'm pretty sure I recorded a lesson transforming this function. But the quartic function goes through 1, 1, and then 2 to the power of 4 is 16, goes through 2, 16, and it's even on both sides. So it goes through negative 1, 1 and negative 2, 16. So it's basically, it's not a parabola. You can think of it as like a squashed down parabola. That's how I think about it. You guys saw that function in your last math course? It's like a squished down parabola. But you can see everything fits together. We have our intercept of 0, 0, our only x-intercept, our only intercept. Our second derivative test failed. We couldn't make any conclusions. But after digging a bit deeper and looking at the concavity, we reasoned out that it's a local minimum, which is consistent with the graph. You guys okay with that one? You know, just anecdotally, even though this warm-up problem had a lot of math, we did a lot of things, we solved a lot of equations, in my opinion, everything was kind of cut and dry. There was a y-intercept. When you took the first derivative and set it to 0 and solved, you got 3 critical points. And when you applied the second derivative test, it was crystal clear, local min, local max, local min. And then when you found inflection points, you set the second derivative to 0, you got 2 different answers, it was clear they were inflection points, and everything kind of fit together. But it's interesting how, just for this simple function, y equals x to the power of 4, maybe things are a bit less clear when you looked at the math. So I wanted to do an example of a graph where we knew what it looked like, but to show you guys where the test breaks down. So a lot of discussion there. Anything you guys want to chat about? I say discussion, mostly me talking. All right, well, let's do another example. This one's a really interesting one. So again, we could just make a table of values here and get us an idea of what this graph looks like. But let's go in blind and see what happens when we apply our algorithm for sketching. So like the first one, for this function, the cube root of x, which let's just maybe for our derivative purposes write as x to the power of a third. Just like the last one, 0, 0 is the only intercept, right? The cube root of 0 is 0. So I'll add that to my graph. All right, let's dive in. Let's look for some critical points. So we've got to find the derivative. So our function is x to the power of 1/3. So the first derivative, bring down the 1/3, x, and then 1/3 minus 1 is minus 2/3. I'll clean that up in a second. But to get the second derivative, I think I'd like to find the second derivative while I have my derivative in that form. Bring down minus 2/3. 1/3 times minus 2/3 is minus 2/9. Minus 2/3 minus 1 is minus 5/3. Aren't you guys glad you did adding, subtracting fractions in grade 9? We're all masters at it. And those are the derivatives. I'm just going to rewrite those in terms of radicals. So the derivative would be 1/3, and then x to the power of 2/3. It would be the third root of x squared. And I think I can zoom in a little bit there. And the second derivative would be minus 2 on top over 9. So x to the power of minus 5/3. The 3 is the root, and the 5 is the power. So it'd be the third root of x to the power 5. So we have our derivatives. Let's find the critical points. I'm going to actually just let you guys talk with your C partners for a second. And I'm just going to drink coffee here and just daydream. Are there any critical points for this function? I'll let you guys chew on that. Are there any critical points? while you guys discuss, I'm going to write the definition of a critical point here. So, you guys recall before there was an OR to this, right? When f prime is undefined. You may be like, Mr. Smith, why didn't we do this earlier when sketching all our polynomials? Well, guys, for polynomials are defined everywhere, right? Their domain is x even any real number. So this wasn't even a consideration, sketching polynomials. But it is here. Now that I've given you guys a definition again, can you discuss, are there any critical points for this function, looking at the derivative? Anything that makes it 0 or makes it undefined? All right, maybe somebody who hasn't helped out yet today? You see a critical point or a critical number? Anything make that first derivative 0 or undefined? 0. Yeah, 0. Yeah, x equals 0 makes that first derivative undefined, right? But like, it's not like there's a vertical asymptote there. We've already established, like when you plug 0 into this function, you get 0. There's a point there. But the derivative is undefined. What does that even mean? Well, let's have a little team talk about that. When you plug in 0, or if you try to the derivative, you basically get 1 over, if you can think of it as 1 divided by a really small number. The second derivative is undefined there. There's a vertical tangent at that point. I'm going to add a little note down here below. You guys should too. I think that font should be okay. So we've just had this discussion. We'll jot it down. We've had the discussion. It'll be recorded forever via this YouTube video in our news feed. But let's just summarize our discussion. X equals 0 makes that first derivative undefined. So what does that mean about the graph? That means that 0, 0, 0, 0 is a critical point with a vertical tangent. The graph's going to kind of be vertical at that point. We'll graph it in a second and see what that looks like. All right, so we've talked about critical points. We found 0, 0. It's a critical point, but it's going to have a vertical tangent. Let's talk about inflection points. Are there any inflection points? So when you guys think about inflection points, so the first thing you think of is, you might think, okay, try setting -2 over 9 times the third root of x to the power of 5 equal to 0. Is there anything that makes that second derivative equal to 0? And there isn't. There's no solutions here. No solutions. Nothing makes that equal to 0 because nothing makes the top 0. But I'll tell you, there is actually an inflection point in this graph. An inflection point doesn't have to be where the second derivative is 0. Let's actually do a little mini numerical investigation here. Just like the last one, can you take the second derivative on to the left of x equals 0? And can you guys take the second derivative to the right of x equals 0? So the third, so -1 to the power of 5 is -1. The third root of -1 is -1. The second derivative to the left of 0 at -1 is -2 over 9. It's concave down. See, excuse me. It's it would be -2 divided by -9. I'm sure you guys would have told me this. That would be +2 over 9. So it's concave up. You know what I was doing there? I got my value and I thought about what the graph looks like and I realized it wasn't fitting. So I went back and caught my mistake. Same thing will happen to you guys. And then when you plug in 1, you get -2 over 9 concave down. So this graph, which is continuous everywhere, the third root of x, you can plug any number you want into here. It's continuous everywhere. Has a vertical tangent at 0, 0. It's concave up to the left. It's concave down to the right. The 0, 0 is an inflection point. And we'll just finish off sketching it. So I might add a little extra note here. At 0, 0, the graph changes concavity. 0, 0 is an inflection point. So what does that mean for the graph? What does the graph look like? Well, let's actually just plug in some values that we know. Make the sketch just by plotting those points, and we'll see that everything kind of fits together. So I might just delete my face for the rest of this video. The cube root function. Well, the cube root of 0 is 0. We've got that point. The cube root of 1 is 1. And the cube root of 8 is 2. So you guys can plot those 3 points, 0, 0, 1, 1, and 8, 2. Also to the left, the cube root of -1 is -1. And the cube root of -8 is -2. And we'll just connect these with a smooth curve, and we'll see that everything fits. So check this out, guys. Concave down to 0, 0, where we have a vertical tangent, and then, concave up, and then concave down forever and ever, amen, to the right. That's the graph of the cube root function. We've got an inflection point at 0, 0, where the second derivative was actually undefined. It's crazy. So if I may, before we wrap this up, I think that, in the warm-up, that curve sketching thing we did, I think that you could get by doing this, just memorizing the steps, and everybody could just memorize the steps and graph a quartic. There was no surprises in this one. Just do the math, grade 10 skills. I think really deep understanding of this stuff comes from examples like we just did. So maybe even tonight, you want to put YouTube on double. How fast can you make YouTube videos go? You put it on the highest speed and maybe rewatch these to make sure you have a good understanding of where these come from and where maybe our second derivative test breaks down, and how it's possible to have an inflection point even if the second derivative isn't 0 there. So I think these would be good ones to go and review just to make sure you have a deep understanding. Okay. Anything you guys want to chat about? Probably not, but I will always ask. All right. So to finish off, a little graphical exercise here where you've got some information about the second derivative, the first derivative, and the original function. And we'll see if you guys can come up with a possible sketch of what this function looks like. We have lots of time, so I'm just going to actually not rush through part A here. And I'm going to let you guys think for these 3 pieces of information. What is this telling you, this telling you, this telling you? And can you give me an idea of what that graph looks like? A possible graph. There are many such graphs. And I'll resist the urge just to do it with you guys right now. What do you think that graph looks like? Okay, I will give you this hint. Remember, original function gives you y values. First derivative, slopes of tangents. Second derivative, concavity. So that's the hint I'll give you. Now I'll let you guys just think on it. I'm still going to just let you guys think on this. So when you guys become teachers, sometimes you'll have silence and you'll feel the urge to fill the silence like I'm doing right now. But sometimes it's best just to let everybody wrestle through something. All right, I've let you struggle enough. Let's pick through these 3 pieces of information and talk about what they mean. This one is kind of a slam dunk. F at minus 3 equals 9. That just means there's a point minus 3, 9. That's the y value when x is minus 3 is 9. So whatever you think the graph looks like, it should pass through minus 3, 9. All right. We've used that piece of information. I'm going to exit out. I've used that piece of information. Second piece of info, the first derivative at minus 3 is equal to 0. Well, that means there must be a horizontal tangent line at x equals minus 3 at that point. I've used that piece of information. The last piece of information, I might get one of you guys to tell me. Charlie. Actually, no inflection points here. No inflection points. Eugenio? Concave down. The second derivative is -2 all the time. This means this function is always concave down. And I love the participation. What kind of graphs do you guys know about that have kind of a single critical point and are always concave down? Aaron. A parabola that opens down with its vertex at minus 3, 9. It's not a complicated sketch. This sketch fits all the bill. I mean, we could probably do a deeper dive in what equation of quadratic function has that second derivative that's exactly -2. But for the purposes of this exercise, this is the thing. Do you understand that the function gives you y values, that the first derivative gives you slopes and tangents, and that the second derivative gives you information about concavity? Can you guys now give me a go? So you've got information about the concavity, and you've got some information about the first derivative. You've got no information about where certain points are, so you have some flexibility. However, the shape of all of our graphs should be kind of identical. Yep. I'm gonna get somebody who hasn't. I'm gonna insist on someone who hasn't helped out yet today. All this information that I've blocked off right here. The second derivative is negative when x is less than -1, and it's positive when x is greater than -1. All of that tells you something specific that we can kind of add to our graph. Anybody looking for someone who hasn't helped out? Maybe we go from concave down to concave up. What does that mean? Yes. Here. We got an inflection point. Where?
-1.
At -1, right? Because it changes concavity at x equals -1. Now, whereabouts? The question doesn't give us any y value at -1, so you can put it wherever you want. I might just plop it down here. I might just put an inflection point here. But no matter what your graph looks like, everybody should have an inflection point. And we also know it's concave down. I don't want to make this too clunky here. I might just put a down and an up. I don't want to, it's already looking pretty clunky. But it goes from concave down to concave up. So now, if we look at this bit of information, f at -3 is equal to 0. Horizontal tangent line. But now, since we know the graph is concave down on this side, that means that that at -3, we can actually say what kind of point it is. Anyone want to volunteer? We have a local max there, a local min there, or an inflection point there when x equals -3. I'll take people repeating if you'd like. Here. Local max, because it's concave down, right? So at -3, we have a local maximum. We better, if I put my inflection point here, I better put my local max somewhere above that. Something like up here at I'll put it at -3.5, but it just has to be above that inflection point so that the graph can be concave down and have that horizontal tangent. And then maybe you see where this is going. F prime at 1 equals to 0. The graph is concave up after -1. At 1, we must have a horizontal tangent. I'll put my point down below here. It just has to be below the inflection point. So the idea here is that this graph would be a cubic function with an inflection point at -1, a local max at -3, a local min at 1. And where are those y values? There's many different possible graphs that we can make. You guys okay with that little exercise there? Good little exercise in my opinion. And I think the practice I gave you from yesterday, I believe the practice has a few of those. But now that we've got some more experience, maybe if you didn't try those or you tried and had a hard time, you can go back at them. All right, so that wraps things up. So